Hello, everybody, and welcome. So our next speaker has been writing software since before the internet was a thing. Everybody, please help me welcome John Anderson with his talk titled Leaky Abstraction and Turing Configuration. John?
Thanks, everyone. Hi, my name is John Anderson. My accent is from South Africa. I am too, weirdly enough. I live in Virginia now. I'm doing this talk because I've noticed a set of patterns that keep showing up in software, in the software I've worked on, and I've not really seen discussion of it in this form. So there are three parts. The first part is leaky abstraction, then configuration languages, then how leaky abstraction pushes configuration towards Turing completeness. The idea of leaky abstraction, oopsies. You're not supposed to see this yet. Now I've just given away my whole talk, great. Okay, now I'm on the right window. The idea of leaky abstractions first showed up in a blog post by Joel Spolsky in 2002. What he said was that. And when I read the blog post, it was mostly about simplifications rather than abstractions. To be fair, that's a fairly common use of abstraction that I've heard a lot. This technology over here is way too complicated. Our new thing just abstracts all of that away. And my inner movie plays out at that point, well, that's very nice, but where does all that abstraction go? What abstract away in that context usually means is we're going to do something that hides away all the messy, annoying setup options that most people never need. And that's quite fine and quite useful most of the time, right up until you really need one of those setup options, and then you find yourself in a situation called lock-in, and you start crafting elaborate workarounds, submitting issues, submitting PRs, and sometimes even providing donations to the project repo. The best definition of abstraction I've been able to come up with is that it's the removal of irrelevant details while simultaneously parameterizing those details. And one can see this with the usual abstractions, data structures, and functions. Data structures generally abstract data, where the data itself is the irrelevant detail. And in sensible languages, you can parameterize a little by type variables, but the data structure itself is the actual parameterization. In the meantime, the actual values are cheerfully ignorable right up until you've got terabytes of the things, and then you find yourself wondering about string dictionaries and other ways to use less memory, and that usually results in you reaching right back into that parameterization that you made and trying to figure out how to do the abstraction better and how to store something other than a string generally. It's kind of weird sometimes, I think, that data, which is the important part, is an irrelevant detail. Functions abstract behavior. Yeah, I know, that's the very lightweight version of functions. But at that level, at the level of the signature, the irrelevant detail is the operation. I mean, you look at that, and I can tell you that it's arithmetic. It's a binary operation closed over num, but that's about all I can tell you. The detail is leaked somewhere. If you're lucky, it has a sensible name. At the level of the actual named function, the exact implementation of the function is the irrelevant detail. For example, absolute value, you could have several different equivalent implementations, but there are usually implicit trade-offs because not every implementation is identical. A classic one is memory usage versus CPU usage. There are others, and it's pretty rare to see those kind of trade-offs parameterized. And that trade-off is exactly what Mr. Spolsky described in his blog post. You can pretend, for example, that standard in is a stream or a reader or whatever your language wants to call it, and you can pretend that a file is also one of those things, right up until you ask that thing for its length, at which point standard in does not have a length. It also doesn't have a name. And there are other examples of this. Here's a couple of other simple ones. You can pretend that an integer is sufficient right up until you need 33 bits or 65 bits. And you can pretend that a float is really a real number right up until the denormals show up. Another example of this kind of thing, but with a different etiology, a different set of reasons, even when the irrelevant parameters, the irrelevant details could be parameterized, they aren't, because systems have external interfaces, and the stability of those external interfaces is valuable. So there's a certain amount of pressure against destabilizing downstream dependencies by parameterizing external interfaces, with the result that whatever leaky abstractions might already be in the system tend to kind of stay there And sometimes they end up showing up in configuration and environment variables in places like that instead of in downstream dependencies. And that right there is what Mr. Spolsky called the law of leaky abstractions, which is basically that when you have these leaky abstraction things, they tend to show up in some other part of the system in some other form. Okay, so data structures and functions are fairly familiar to most of us. I'm going to walk through something that's possibly a little less familiar, but it shouldn't be completely unfamiliar. That's a graph. And it's not entirely the same as a graph in math, because in math you can just imagine the connections, but in programming you have to actually store the edges and the nodes somewhere. If you're not familiar with these things, the little circly things with numbers in it, those are the nodes. The edges are the black lines that connect them. And in this particular graph, you can start at a node, and you can follow black lines and come all the way back to the node, and that's called a cycle, and you probably know about these things. Of course, you may also know that for any particular graph, there's a thing called a spanning tree, where you remove some of the nodes. In this case, the orange edges, the orange dotted edges, are the edges that have been removed. And the point of removing these is that there are now no more cycles, firstly. And secondly, you can pick any node and pick any other node, and you can follow black lines across from the one to the other, which means it's still connected. And you might be thinking to yourself, but is that the only set of edges I can remove? Well, no, it isn't. There are several sets of edges that can be removed, because depending on the interconnectedness of the graph, you can have several spanning trees. So I've done another one just for fun. Watch the edges going to nodes 9 and 11. And you'll see that there are different edges, but those two properties still remain, which is that the graph is connected, and there's still a path from one to the other, and there are no cycles. Those are the two different properties. All right, so I'm just going to go back and forth a few times so that you can see those if you want to. There's one other critical thing here, which is that I'm going to go back to the graph now. You'll see that the set of nodes remains entirely the same. I've even left them in the same places. And here's something that's possibly not entirely familiar, is that you can think of a graph as a composition of its spanning trees. And you do that by union of edge sets. That dot, dot, dot over there is you imagining all the other spanning trees that might exist here. And from this vantage point, it's pretty easy to see that any given tree, pick a tree, it could be just one of a set of spanning trees comprising a graph that you don't know about yet. And in that case, that one tree would be something like a leaky abstraction of the graph, where the irrelevant details are the edges. Okay, this is all getting very serious, so I think we should have a comedic break now. And if you don't find that funny, that's fine. I actually have a dad joke license for these. It arrived in the mail when my first kid was born. I mean, it's nice and mystical and all, but there's actually a real point in here, which is that data only has meaning when it's related to other data. And ultimately, it's the meaning we're after. The test for that assertion would be the existence of some datum where it has meaning without relationships to other data. And if you can find one of these, I'm dead curious, maybe after the talk, because I thought about this for some time, and I couldn't come up with something. In other words, just one datum alone that has meaning without relationships to other things. Anyway, coming back from philosophy to the subject at hand, you need the relationships. Those depend on the data. To work on the data, you have to transmit it, even if it's just from memory to hard drive. And as far as I know, there's no way to transmit data apart from serializing it. So I'm going to move on to serialization of trees, which is code, which is the stuff most of us edit every day. And I'm going to call it the serialized text form of what I'm going to call containment trees. Containment because, loosely, files contain modules, modules contain functions, functions contain expressions. Parents contain children. Child node is not just connected to parent, it's inside parent. From a graph point of view, the edges between parents and children are implicit in the containment. So they don't need to be specified separately, which is kind of convenient. Syntax delimits the containment. You can see that in the sort of minified version that I've put in really small text across the bottom, because you've all seen minified code anyway. The point there is that at the level of the actual text, the the data for the child node is literally inside the delimiters for the parent node. And often those are delimited with braces or parentheses or begin end keywords or something like that. You know the drill. But there are actually two trees here. The one is this character level containment structure that I'm talking about. And the other one is the logical tree that you put in there, which is, in this case, some kind of JSON. And data languages often work the same way. JSON, YAML, TOML, XML, HTML, S expressions, and so on. They all express these logical trees inside of containment structures. The parent contains the child. The root is always the top level, and that's part of why I chose JSON here, because sometimes the top level is a little obscured, but in JSON it's always, almost always, a curly bracket, a curly brace, or a square bracket. Sometimes you have plain values, you can, but then it's not a tree, and it's not interesting for this talk. And you might have noticed that there are no dotted lines here. That'll become important just now. All right, I'm going to go on a slight tangent for a moment. There's a book called Concepts, Techniques, and Models of Computer Programming, and that's quite a mouthful, so I'm just going to call it CTM. It was published in 2004. The basic idea in that book is that every programming language implements a set of concepts, and groupings of concepts are called paradigms, and paradigms are the usual suspect: object orientation, functional programming, logical programming, imperative programming. Obviously, there's going to be overlap between them, like a lot of languages implement mutable state, which is one of the concepts in the book. And obviously, not every programming language implements the full set of concepts for the paradigm that it's generally associated with. Anyway, that's just to explain that. The important part is, I have a little pointery thing here. The important part is that, the descriptive declarative paradigm. And that's very similar to what I've been talking about as data languages. In that paradigm, to express data, at minimum, one needs only values and sequences. And if you want to know how that works, you just have to ask S expressions. Hey, S expressions, how do you express a key value structure using only values and sequences? Well, you see, it's very simple. You use a list. A list contains several elements, each of which is itself a list. It's very beautifully recursive. Each one of those elements is a list. I said that already. It contains exactly two elements, which is why we call it a tuple. Motorcyclists and surfers have been known to call it a tuple. Each tuple contains, as its first element, the key, and as its second element, another value, which may itself be a list. It's beautifully recursive. It's the most beautiful recursion you've ever seen. Thanks, S expressions. That's cool. But I'm still going to say that a tree value structure is not exactly the same as a list of pairs. Luckily, we have JSON and YAML TOML, which express key values natively. So they do express some things natively. This containment tree thing that I've been talking about has a quite strong limitation that two different parent nodes can't contain a single child node. It's kind of obvious. If you've got a parent node here, and you've got a parent node here, and that parent node has a child node, and that parent node has a child node, those things are inside of their parents, and they can't possibly be a shared thing. They can be identical copies of the same text, but they can't be the same thing. I think that's kind of obvious. So if the meaning of your logical structure, this one, for example, needs to include additional connections between things, it's going to need the data language to support name bindings, in other words, references, because the containment cannot contain the same data. So unsurprisingly, CTM includes name bindings in its descriptive declarative paradigm. Do any of JSON, YAML, TOML, etc. natively support name bindings? Well, mostly no. YAML kind of supports them with anchors and aliases, but the standard doesn't actually mandate whether aliases should be treated as shared things or as copies. And I've seen in a couple of experiments I did that they're often treated as copies. Obviously, all of these languages, JSON, YAML, TOML, and so on, you can construct references in the data itself using, for example, ID keys. I mean, you can see this in HTML where you have an ID equals whatever. That's actually a reference to some other node somewhere else in the HTML DOM. And constructing references this way obviously induces the need to resolve those references, and the data language, JSON, YAML, TOML, can't do that. So that resolution of references has to be implemented in something else, some other language. It has to be computed by the program making use of the configuration. Okay, so this is obviously a Docker Compose file. And so it's an example of the structure, the tree structure with references. You might also be able to see that it has a resemblance to those spanning trees with the dotted lines in it. Okay, so where are the references then? Well, if you look over here, they've been cunningly hidden inside of strings because that shared storage over there refers to this shared storage over here. And there are 3 of those references. That's what I've put in the diagram. They all refer to the shared storage. The shared storage is a thing called a volume. You can put values in it. You can have as many volumes as you want in a Docker Compose file. And here's another example with 2 volumes. But you can't just create any references in a Docker Compose. You can only create references in relation to volumes and a couple of other things called depends on and extends and external links. And actually, you can parameterize some of those links, which is kind of weird because they're kind of like functions, but that's a rabbit hole I'm not going down in this talk. They're all storage locations. Of course, from the point of view of this code over here, you can't actually put anything in them. If you want to put something in those storage locations, you've got to run this file in its execution context, which is Docker Compose. So the question now becomes, what kind of work does Docker Compose need to do to work with these configuration trees? In the very simplest case, and I've shown that on the right-hand side there, you can turn a tree into a set of paths, at which point retrieving a value from that tree just means following a path down to the leaf node, and there's your value. And following a path is basically sequence matching, which is basically the same as matching a string against a regular expression, except where the regular expression doesn't have any of the usual regular expression stuff, in other words, wildcards and repetition operators. And a regular expression is generally regarded as the same level of complexity as a thing called a finite automaton. So matching paths inside of a configuration file is a level of complexity down from a finite automaton. Okay, that's nice. There might be other cases. For example, if you wanted to find all of the values of the container name over here. In the native structure, you'd have to traverse the tree to find all the container names. To traverse a tree, you need a stack so that you can backtrack when you don't find it. And that thing's called a push-down automaton, which is generally regarded as one step up of complexity from the finite automaton. So can I call this push-down automaton a graph hopper yet? What? What is he talking about? Did you pay attention to the dad jokes? Okay, so there's the push-down automaton. The most complex case with resolving references in your tree. The Docker Compose must now read the tree, find the references, and then resolve the references. And a push-down automaton is not sufficient for that. And so apparently this graph hopper thing, which I've just invented, is more complex than a push-down automaton. Obviously, I've modified this diagram a little from the original written in 2004 because it's now 20 years later. And we're only really concerned about those things, and you might see a couple of Easter eggs. At this point, we've graph hoppered right over that dotted line at the top to here where it says Turing complete. And basically, in this diagram, Turing complete means languages that can compute. None of the languages in descriptive declarative paradigm can compute. That's the purpose of that paradigm. It's intended to be not computable. The modern way of saying that is configuration should be inert. By now in the talk, some people are probably wondering why I haven't talked about DAL and Q and Nickel and languages like that, which are explicitly designed for intentionally limited computation on configuration data. Well, the answer to that is pretty simple. I haven't really worked with them. I've looked at DAL a couple of times, but it never quite seemed to be the right fit for the thing I was trying to do at the time. I did do a little experiment with it to see if it could do this resolution of references thing I've been talking about. But that bumped right into the computations that are intentionally prohibited in the language, and I suspect that the best you could do with that anyway would be the construction of another spanning tree, which kind of doesn't help the problem of resolving references. So it looks to me that if you want to make use of this tree with references thing, where you want to have the succinctness of expressing the parent-child relationships in one of these containment trees, but you also need the references to add additional expressivity to your data, you're going to need to do some kind of computation in a Turing complete language somewhere along the line. But that Turing complete computation is not exactly the same as your application itself. It's a bit of a difference between the functionalities there, and I kind of think of it sitting somewhere between the configuration data on the one hand and the configuration computation here, and then your application proper over there. So I guess the question then becomes, what kinds of things would one see in a configuration layer? And you can tell that this talk is starting to wind down a little because the slides are going gray. And also, that data is what I mean by data tends to become graph-shaped. There's no good tree that you can use to express all of that. So I've only got 5 minutes left. So there's two options here. If you have burning questions and comments, now might be a good time to ask them. Otherwise, I can step you through some of the things in this tree, which is basically just paths and path retrieval and tree traversal. So before we run out of time, do you have any questions and comments? You can feel free to tell me, no, you're complete, this is nonsense. What are you talking about even? Or if you want clarification on anything, or...
The one part when you had the different... Oh, right. The one part of the talk earlier where you had the different spanning trees and you were unioning them, I missed the significance in relation to build systems. So I was wondering if you could clarify that.
Well, it's kind of not specific to build systems, but I've noticed in data that you often arrange a tree along sort of one main axis. You tend to put your data into the tree in a particular way. And a lot of the time, there are relationships in the data, which is because the containment tree, it can only support one logical tree. You can only get one tree into that containment structure. So you often need to have other edges referring to other bits of the containment tree. And those kind of go missing. And the only way to have those, the only way to express those that I've been able to find is these references that I'm talking about.
That makes sense. Thank you.
Anything else? I think that hand went up momentarily first.
Sure. What was the book you referenced earlier in the talk?
It was called Concepts, Techniques, and Models of Computer Programming. And the authors are Peter Van Roy and Saif Hariri. I'll post it on the forum at some point.
Thank you.
There was a question there as well.
I was wondering if you could briefly comment on how this might relate to a declarative or data flow model like you might see with something like Excel at the end of the day, where you have you have reference updates back in your build tree that get pushed forward as you need them.
I'm guessing, okay, I haven't really thought about it from that angle, but I'm guessing that if you had a tree structure, the advantage of a tree structure is you always know when it ends. You can do basically what amounts to a linear search through it. So you did a depth first search or a breadth first search, you come to an end. Whereas with graph-shaped structures, there's extra work you have to do. You have to basically there's two options. You either have to create one of the spanning trees so that you can do a tree traversal on that, or you have to do a breadth first or depth first search where you also have to track the visited nodes. So I'm guessing that if there is a graph of dependencies, that you would have to track which nodes have already been visited in order to know which ones have been updated in any one particular run. How you'd link that up with data flow, I guess you would need to track which values have changed, which would substantially reduce the number of nodes you have to visit and process, I'm guessing. Does that make sense?
Yes, thank you.
Any other questions and comments? How much time do I still have left? 2 minutes. All right, so the other point that I wanted to make here was that, firstly, I've colored those yellow as dynamic languages, and usually any one of these dynamic languages will cheerfully parse any one of YAML, TOML, JSON, even XML into some structure of nested arrays and dictionaries, which is usually pretty trivial to either do that path retrieval I'm talking about, or you can do tree traversal on those. In fact, in Ruby, I happen to know there's a method called dig, Ruby's down here at the bottom, that takes a path, basically. It's in the form of an array, but it's a path, and that will give you back a value from the nested arrays and hashes, dictionaries are called in Ruby. So that's the one point. The other point is XML has a thing called XPath, which is basically this path retrieval, but on steroids, because you get wildcards, you get repetition operators, you get node relatedness connections, and it's pretty useful. Of course, the drawback is you now have to get your data into an XML DOM, and there's a reason that XML is deeply unpopular. The other interesting thing there is that there's a thing called JSON path, which you can find, which is somewhat less powerful than XPath, but not so as you'd really notice. Then typed languages, you'll often find that when you parse these things, you end up with some kind of top-level sum type. Those are very amenable to doing this tree traversal I've been talking about, or for doing at least the path retrieval I've been talking about, and the tree traversal. C++, I'm not so sure about. You probably end up stuck with abstract classes there. But the rest will give you some types. And of course, then there's deserialization into your own set of types. And ironically, that seems to make the path traversals and the tree traversals harder. Or it kind of shunts the tree traversals into the type system itself, which is not great sometimes, but it's kind of ironic. Then the last one is over here. JSON has a pointer function, which is basically an implementation of JSON pointer, which is exactly this tree path retrieval. And that's basically it. And I'm just going to show you the summary. Two last points. The leaky abstractions show up in lots of forms. You might want to keep an eye on them. It's kind of interesting how they work. This tree with references structure, you might have noticed, is not only for configuration. And the last thing I'm going to say is that I'm always on the lookout for interesting work. So if you might have some of that, I'd be happy to talk to you. And that's all, folks.